Hello everyone. In today's lectures, we are continuing to studying the perturbation theory. In the previous lectures, we have solved the problems with a Gn0 is a En0 is a Gn fold degeneracy. Under this sub-eigenspace, we calculate the problems of the eigenvalue problems of the H1 Enx 0 equals to Enx 1 Enx 0. The eigenvalue problems, and we assumed that the Enx 1 are pairwise different. Which means H1 eliminate the degeneracy. In today's lecture, I will continue to introduce if H1 does not eliminate the degeneracy. This is very useful to calculate the effective Hamiltonian of the many systems. Effective Hamiltonian of the many-body systems. So, first of all, we assumed Enx1 is a Gnx fold for Gnx fold degenerate corresponding to the eigen fold degenerate of the eigen Okay, before we discuss, we must the eigenvalue problems there, and we assumed Enx1 is the Gnx fold degenerates. And the corresponding eigenstates are Enx alpha 0. The label alpha represents the different eigenstate correspond to the same eigenvalue Enx1. So we have the equations H1 x on if we restrict on this sub eigenspace. Enx alpha 0 equals to Enx 1 Enx alpha 0 alpha equals to 1 and Gnx. So we still have the basic orthonormal relations, that is Enx alpha 0 Enx beta 0 delta alpha beta. And for y not equals to x, we still have the relation ENY0 H1 Enx alpha 0 equals to 0. First of all, we consider the first order perturbation. In the first order perturbation, we have the basic equations Ax alpha 1. This is the first order perturbation. The plus Nx alpha 1 Enx alpha 0 equals to 0 and x alpha 1 plus Enx 1 Enx alpha 0. And we want to find just as before, we first left action on the left act the cat on this equation. Let's look at what can we get. Let's have a C. H0 ENX alpha 1 plus EMY m does not equal to n. Equals to in x for 0. By orthonormal relation, this one equals to 0 vanished, and these two and x vanishes, and then this one equals to em 0 emy 0 alpha 1. So we find the inner product eny 0 and enx alpha 1. Their inner product equals to en0 minus em0 with emy 0 h1 enx alpha 0. This is our first formula. Then we left act on the state enx alpha. You can see enx alpha 0 h0 enx alpha 1 plus enx alpha 0 h1 enx alpha 0 equals to en0 enx alpha 0, and the inner product of the enx alpha 0 and enx alpha 1 plus enx 1 enx alpha 0 alpha 1, and we have the relation. Let's observe this, and we can find these two parts will be cancelled. These two terms are because this h0 acts on the left state vector, and it's the eigenstate, so it equals to en0. So these two terms can be cancelled. So, and this term, because here is 0, not 1, and this term equals to 1. So the first order, the energy correction equals to enx alpha 0 h1 enx alpha 0. This corresponds with our basic assumption. The basic assumptions. These two set And so the ENX1 satisfies the definition here. Then we consider the second order perturbation. Second order, the basic equations is the H0 ENX alpha 2 plus H1 ENX alpha 1 equals to EN0 and X alpha 2 plus ENX1 ENX alpha 1 plus ENX alpha 2 ENX alpha 0. And we first of all left act on, let the state ENZ act from the left. This does not equals to X. So we have ENZ 0. ENZ 0 H1 ENX alpha 1 equals to N0 ENZ X alpha 2 plus ENX1 and C0 ENX alpha 1 plus NX alpha 2 Z0 ENX alpha 0. And we can find by the autonomial relations this equals to 0, and these two terms will be vanished because the ENZ is the eigenstate of the H0. Then these two equals to EN0. So we have simplified these equations. H1 ENX alpha 1 equals to ENX1 ENZ 0 and X alpha 1. And we can calculate, we just expand and X alpha 1 equals to sigma. We can represent this by the there's order we can represent by this by the eigenvectors of the H0. So it equals to EMY0 ENX alpha first sigma y not equal to X and Y0 ENX alpha M plus sigma gamma beta. We use the beta and X beta. So we can find and this term equals to z0 y0. Plus the last term. Now we observe these three terms. First of all, in these two terms will vanish. Okay, let's observe this term equals to this term equals to delta y z and y0. So this sum one not equals to 0. So this term will equals to, and the delta function will cancel the summation. So this equals to e and z first. And we can find this term will vanish because these two because the x will not equals to z because there is no summation of the x z term. So delta x z, because z not equals to x, so this term vanish. So these equations can be write in this way. We find sum n not equals to n and z0 h1 e y0 y0 e n x alpha 1 plus e n z1 e n z1 the e n x e n z0 x alpha 1 equals to e n x 1 e n z0 the e n x alpha 1. So we calculate find the inner product e n z0 the e n x alpha 1 equals to since y z0 e n y0 e n x1 minus e n z1. We have the e n y0 e n x alpha, and this term we have calculated before. This is our first relations. So this term equals to this term equals to E my, this is M0 H1 ENX alpha 0 EM0 minus EN0. So we have find the first order. This is the first order energy correction. This is the first order energy correction, and the first order state corrections can be write as alpha 1 equals to 7 summation from the M y E M y 0 plus z not equals to x and z0 E n x alpha E n z0. Actually, we can find that this term is actually much less than, it's much smaller than this term, because h1, because this term equals to this is quite small, and there are two. This is order lambda, here is lambda, and the way over. This is quite big, but this one is relatively small. So, oh no, actually these two terms are, I think they take some similar values. So n beta not equals to alpha E n x beta 0 x alpha 0. First, E n x beta 0. Actually, in many problems, these terms are less important when we solved some real problems. So we just give these two terms, and then we'll continue to find the second order energy perturbation if the H1 does not eliminate the degeneracy, and if the subspace of the degeneracy is the problem that we are interested. So let's continue. I think I didn't explain it well because my English is not good, and this is quite really complicated. So here we want to derive the effective Hamiltonian. We left act nx gamma 0 on the basic equations of the second order perturbation. So we have 1 E nx alpha 1 equals to some not equals to ny x gamma 0 E my 0 my 0 Okay, we first observe on the oh no, I just okay, sorry, I made I just write the wrong equations. Enx 0 enx alpha 2 plus enx gamma 0 1 enx alpha first to en0 enx gamma 0 and enx alpha 2 plus enx 1 enx gamma 0 enx alpha 1 plus enx alpha 2 enx gamma 0 enx alpha 0. So in these two terms will be cancelled because this is the eigenstate of the H0. And this term equals to delta function then R alpha gamma. So this equation becomes x gamma 0 H1 enx alpha 1 equals to enx first plus x alpha 2 delta alpha gamma. And with the first term, we expanded the enx alpha. This equals to gamma 0 my 0 x gamma 0 H1 ny 0 x alpha 1. Let's observe this. This term equals to delta x y because by the basic orthonormal relations, but the y does not equals to x, so this term vanished. And here, this term equals to enx 1 delta beta gamma, and these two terms, delta function and the summation, will be cancelled. So this term equals to enx 1 enx gamma 0 and x alpha 1. And this term and these two terms will be vanished. So only these terms remains. So we have sigma not equals to ny summation Enx gamma 0 EMY 0. This term has been calculated from the first order perturbation equals to EMY 0 1 ENX M0 0 equals to ENX alpha 2 delta alpha So if we restrict on the sub-eigenspace of the NX alpha, we have the ENX gamma 0 summation m not equals to NYH1 my0 my gamma delta gamma. We find this is the equations of the eigenvalue problems. So we can define the effective Hamiltonian. Equals to this is the formula of the second order perturbation theory, the effective Hamiltonian. And this satisfies the definition of the many other derive this by the we can also derive these equations by using the Green's function, but this is I just derived it from the traditional time-independent perturbation theory by series expansions. Okay, that's it.